stability analysis of hexagonal close-packed crystal structure and a finite string. And here you won't hear anything about numerical simulations. A couple of words about motivation. In order to ensure the variabilities of state of the material and to predict the limit states, it's necessary to introduce the models of fracture at a different scale, taking into account the internal structure. And it's particularly important to introduce the models of the materials with the ideal geometric structure. Because, for example, given the advanced nanotechnology, simple crystals are becoming more and more demanded, and the strength is close to theoretical one, or ideal strength. First, when we build the models on different scales, we start with linear analysis, where we try to obtain the link between micro and macro mechanical characteristics to calibrate the models and to be able to interpret the experimental results and to carry out the comparison with the calculations in engineering simulation software, which is traditional classical continuum methods. And when we pass over to the linear analysis, coming closer to fracture, we can say that fracture can be associated with a stability loss, but the stability loss may cause not only fracture but phase transitions. And when we deal with stability problems and do stability analysis, we finally come to the increase of the reliability or the determination of critical loads of the material. But that were more general words. In this particular work, we'll focus on diatomic crystal lattice, multilattice, and we'll stick only to pair force interaction hypothesis to obtain more results analytically. And the aim of this work, this analysis, is to get the stability region of the object in the string space. Let us introduce some notation. So we have a crystal lattice, something like this. We use the origin and we draw radius vectors. The units of cell, for example, for triangular lattice is this one, and we need both current and reference configurations. Then we introduce the interaction. Let's take two particles, two nodes of the lattice. The interaction depends only on the relative position of the particles, that's all. And the elastic characteristic, for example, depend only on longitudinal stiffness of the bond. And it's proved that this type of interaction ensures stability of closed-packed structures of equilibrium. And the example is Lennard-Jones potential. It has only two parameters, depth of the well and the equilibrium distance of the potential. That's what we need. And the simplest we can imagine. As for closed-packed structures, there are two widespread structures that are typical for metals: face-centered cubic and hexagonal close-packed. Face-centered cubic, as it is obvious from its name, possesses the cubic symmetry. It can be visible if you look at it from this angle. But as it's close-packed, you can visualize the packing of hot spheres, like this. Face-centered cubic lattice coincides with its Bravais lattice, so it's simple. And hexagonal close-packed consists of two sublattices, A and B, and its diatomic multilattice consists of two sublattices. For multilattices, the geometry should be written in this way. The connection between current and reference configuration is accomplished not only with strain gradient, strain gradient is transposed, but I think you get it, and we add the sublattice shift. There are a couple of ways to introduce the Cauchy-Bonne rule, but we stick to this one. In case of homogeneous deformation, each sublattice remains in equilibrium. I will show it later. And to determine the sublattice shift, this vector psi, we need additional equilibrium condition, which looks the following way. I made a mistake on the previous slide. I didn't introduce the strain energy properly. It's a Cauchy-Born strain energy. It's just the sum of the potentials of all bonds that we can take into consideration. Then we take the second duration of strain energy at the equilibrium, and where u are terms of fourth, third, and second rank, just derivatives, nothing difficult. And here, that's what they look like in terms of current and reference configuration vectors. And all this complex stuff depends only on the geometry, that was introduced in the previous slide. Just it may look a bit too large. And here the tensor product is omitted. So here, and here we have tensor product. And the stability criterion, we use the positivity of the second duration of the strain energy, which yields to the two inequalities. This one and this one, because we assume that this and this are independent. And these two inequalities should hold for all possible variations of strain gradient and of modified sublattice shift. If we had a simple lattice, the sublattice shift wouldn't exist. It would be equal to 0. And thus, the tensor Q will have the Q asterisk, will be equal to tensor Q, which in turn is the second derivative of the strain energy. And the stability criterion would yield the strong ellipticity condition, which in our case, for infinite lattice, we don't account for boundary conditions, is not only necessary stability condition, but also sufficient condition. But we have a complex diatomic lattice. HCP structure looks this way. The solid lines denote the unit cell. And this ratio has the specific value. It's valid for, I think, magnesium. For other HCP metals, it may vary, but we will take the ideal geometry again for the sake of simplicity. Let us introduce the following strain gradient with the two axes which lie in the plane of the transverse isotropy of the lattice, and 3 will be the axis of transverse isotropy. So 1, 2, 3 are the direction of the eigenvector of the strain, eigenvectors of the strain gradient. Let's start with the equilibrium condition. Each sublattice of the diatomic lattice is simple lattice, so for which we can draw the following picture. By this picture, I mean that every force, because we have pair force interaction, has a force of the same magnitude but different direction. So that each sublattice is in equilibrium at any arbitrary homogeneous strain. And for sublattice shift, we should solve the set of equations. And for this specific strain gradient, from the symmetry of the lattice, we can judge that the sublattice shift will be directed, will lie in the plane of isotropy, and will be directed along the axis number 2. So, then to stability conditions. We have two inequalities which have to be satisfied. And they yield to the demand of the positive definitenesses of two tensors of second rank. With Q2, it's obvious. With Q4, we have to check the validity of this inequality for each strain gradient. We should use the Monte Carlo method, and well, it's so visible on this page. The only thing that we should do is to think about the convergence of the method. So, what to expect as a stability region? Let's first turn to face-centered qubit. It's simple lattice, and something that has been already done about. We can introduce two sets of axes. First, it is face-centered cubic, it's visible as face-centered cubic, and the axes are directed along the axis of cubic symmetry. And this is also part of the face-centered cubic lattice, but the axes are directed in the plane of the transverse isotropy and along the axis. And the stability regions in these two cases will look the following way. That's for Lagrange potential. As you see, the stress-free configuration with epsilons equal to 0 is somewhere here, somewhere here. So that's the stability region for the FCC in the following straight spaces. So some two cross sections of the full 6-dimensional stability region of FCC lattice. And you see that there is a tiny tail leading us to the compression of the material into the point, but it doesn't have much physical sense because it actually is a line, and you can't accomplish the compression with such precision. So the real stability region ends somewhere here. And that's what we got for HCP. You can have a look. There are two of them. We could have expected that the stability region for HCP will look the same way as for FCC, more or less, because they are two close packed lattices. What else would have happened? But not. And when we did some examination of the lattice, we understood that the stress-free HCP is somewhere here. And somewhere here is something that looks like an FCC. So, doing some geometry, we understood that somewhere in the center of the second zone, we have a stress-free FCC, and that's its coordinates, and that's the corresponding sublattice shift. I hope you understand where is everything turning. So it's axis number 2, and axis 1 and 3 are turning. And the green spheres are first coordinational spheres of HCP and FCC respectively. So what's that? Let us draw the dependence of the non-zero component of the dimensionless non-zero component of the sublattice shift on the line that connects two stress-free configurations. And that's what we see. Here it's 0. We start from the stress-free HCP. Then we stretch, but we have this transformation is strain-induced. We don't talk about stresses. We somehow stretch, and starting from here, near the border, the shift becomes constant. It means that two sublattices used to move along each other, and at some point they stopped moving along each other, and they started straining all together. It means that the complex lattice really became a simple one. And somewhere here we get the stress-free configuration. That's what we see. And there is this strain energy profile on this line, and we see two minima. They are the same depth because the two lattices are close packed. They have the same continuational numbers. It means that they should have the same strain energy, and the influence of the farther neighbors, which a little bit differs, starting from the third sphere, is negligible. That's what we see. The stability regions are hatched here, and the two minima corresponding to two types of lattice. Now comes the conclusion. The obtained conditions, in fact, are valid not only for HCP, they are valid for any diatomic lattice in any dimension, provided that the interaction between the particles is all the same, and the interaction is not a pair force interaction. but it can be easily extended to the cases of multilattices. We introduce more shifts. And to more sophisticated interaction laws, it's not so straightforward, but it's also possible. And the technique allows us to obtain stability region in straight space for static material. It means that we can describe various training paths. In literature, usually only one or two paths are described, not one line, but it is investigated. Here, we didn't have much investigation of this or that training path, only one single line, but we have the possibility to draw any curve in that space and have a look at it. And this possibility is illustrated by the analysis of two stability domains where we actually saw stress-free complex lattice and the process of turning it to stress-free simple lattice. Thank you for your attention.
Thank you very much. Some questions? Yes?
That's it. What characteristics of the interaction potential are important here? I mean, you say you can explain that it's true for any pairwise interaction, so which characteristics are important for, say, first and secondary rate or anything else?
Nothing, only first and second derivative of the potential energy. Of course, what can be regulated? The walls of the potential well. They can be, the well can be widened.
Yes, but I mean, you're obtaining exactly the same picture. For we are going to the same picture for the class of potentials.
This is for me potential, I think. The Leonard-Jones potential is the particular case. For Morse potential, we'll have some problems because the base-centered cubic lattice will appear in some parts. But Leonard-Jones and me potential don't allow the existence of the BCC lattice. So the pair force interaction is applicable to closed-back structures mostly. And I don't know anything real except from FCC and HCP.
So, can you think of a kinetic description of the transition from your HCP lattice to the FCC lattice?
Kinetic.
So, this is kinematic or geometry, what you described here?
I described the geometry. I don't talk about stresses at all. We can try to think of the stress-induced transformation, but I don't see any, up to now, I don't see any physical meaning like uniaxial transitional, that stuff. But we can think about it. And I think that temperature should be introduced into the model. Probably we can introduce it in the parameters of the potential. Maybe not. I hope not.
Can we go back to your conclusion slide?
Sorry, I'll try.
Yes. Can you explain or elaborate the first conclusion? You said obtained stability conditions are valid in space of any dimension for any. So what do you mean by
space of any dimension? It's
which stability conditions? The picture that you've shown, or the two in it?
The picture that I showed was the application to the HCP lattice.
Right.
The condition is positive definiteness
Of the second variation.
of the second variation.
From a certain point of view, the stability is very good, but non-stability may be more interesting. In this case, the loss of electricity can be interpreted like a slipping in some directions. Do you think about this possibility to describe some, let's say, models related to crystal plasticity?
Well, perhaps because we see the real shift of the sublattices during the stream, but this has to be thought over.
Do you observe some twinning also? Because you have a phase transformation
I don't know anything about the evolution of the system. It's not a numerical experiment. I just say, supposing my lattice is strained this way.
Yeah,
That
but
will-
you can get a twin also if
I
you
can't get a
if you deform the lattice.
no, everything is homogeneous. How can I get a twin?
I mean, you get a new crystal structure. You could get also the mirror crystal by
No.
proper.
Well, I think when I am somewhere here,
Yeah.
I can get a twin. But the system has to evolve. But for me, I'm in quasi-status. How can I get a twin?
By stability.
Yes, but not within this particular investigation.
Other question? If not, thank you very much again.